Senior Plasma Physics, Lecture 15. We're going to examine the hydrodynamics of magnetized plasmas, which is commonly known as Magnetohydrodynamics, or MHD for short. The term MHD implies that we are dealing with low-frequency interactions of the plasma with the magnetic field. We've already seen one example of this in a previous lecture, which is the alphane wave. Ideal MHD. Recall that Ohm's law for a normal conductor can be written like this, where E is the electric field strength, eta is the resistivity, and J is the current density. It can be shown that if there is a magnetic field also applied, that a generalized Ohm's law can be written like this. This can be derived from the fluid equations. Under some circumstances, we want to regard the plasma as essentially collisionless. So we say that there is no resistivity, and we write the so-called ideal MHD equation, given by this. Let's now derive an expression for the pressure applied on a plasma by a magnetic field. Recall the momentum equation from the fluid model of a plasma, given by this. In the steady state, where the drift velocity u is constant, we can let the derivative be zero. That means the right-hand side of the momentum equation can be written as follows. The left-hand side is the familiar Lorentz force term, without an electric field in this case, and it's equal to the force due to the plasma pressure gradient. Now let's substitute into it this Maxwell equation. We replace J by the Maxwell equation and rearrange, and we end up with this. Now the two cross products can be simplified to this term. This is obtained from vector identities that you can find in any vector calculus book. Let's rearrange this equation as follows. What you'll notice is P, the plasma pressure term, that is the pressure applied by the particles in the plasma, and this term is also a pressure term. It's the pressure applied by the magnetic field on the plasma. If we assume we have a situation where the magnetic field B does not change in its own direction, so that is, its gradient is zero, then we can set the right-hand term to zero. What this says is that for the left-hand side to equal to zero, that means the expression in brackets must be a constant. Keeping the two pressures constant has implications to the pressure inside a plasma. Take this cylindrical plasma where the magnetic field is along its axis. Assume the plasma has a high enough density such that you get significant diamagnetic fields in the center as shown. That means the magnetic field at the center will be reduced. So if there's a low magnetic field at the center, there must be a high particle pressure P at that point. However, if we now move out towards the edge of the plasma, where the diamagnetic effects aren't as strong, so the magnetic field becomes higher, that means now the particle pressure P must be lower to maintain the constant sum of particle and magnetic field pressures. So the relative values of the particle pressure and the magnetic pressure are quite significant in plasma fusion research. So we define a parameter beta, which is the ratio of the particle pressure to the magnetic pressure, given mathematically by this. The pressure in the plasma is caused by all species. For example, the electrons would cause a pressure and so would the ions. So P is really the sum of all particle pressures. We can rewrite this equation as follows, where we've used the ideal gas law P equals nKT for each species of the plasma.